Hello everyone, I'm Yang from DP1 Computer Science. The title of today's computer lab is Packets of Literature. First of all, what is a packet? In computer science, a packet is a small unit of data sent over a network. It is used to break down large data sets into manageable pieces for efficient transmission between devices. These packets are then reassembled at the destination to recreate the original data. In this lab, we are given a set of packets of data as binary files. However, within these binary files, there are corrupted ones and uncorrupted ones. The problem can be divided into two parts. For part A, we are tasked to identify all corrupted packets and state their source, destination, checksum, and expected checksum. For part B of the task, we are to construct the messages in the uncorrupted packets and state their source, destination, and the original message. The structure of the packets is a sequence of 35 bytes with this structure. The first 5 bytes is a header, and the remaining 30 bytes makes up the payload space of the packet. Here is an example of one of the packets given. As we can see, there is a total of 35 bytes in this packet. The first byte consists of two nibbles. The first nibble is the source of the packet, and the second nibble is the destination of the packet. The second byte contains the number of parts the message to be constructed has, and the third byte contains the part index, which is the position in the constructed message that this packet's data belongs. The fourth byte contains the length of the data stored in the packet, which is the number of bytes in the payload space that are used for the actual payload. The fifth byte contains a checksum, which is the sum of the data stored in the packet's payload modulo 256, which can be used to check whether the data in the packet has been corrupted. And starting from the sixth byte, which is at index 5, to the very end of the packet, is the payload space. In the context of this problem, the payload represents ASCII characters of a text message. Here is the program that I designed to solve part A of the problem. The program begins by setting up a directory path to the packets folder using the pathlib module, which is this part of the code, and initializes a counter to keep track of the number of corrupted packets, which is this part. It then iterates over all the files in the directory, opening each file in the binary mode by using RB, and reading its content as a list of bytes, which is this part of the code. This allows the program to extract specific pieces of information from each packet. Then, this part of the code determines the destination and source of each packet. Notice that the first byte in the packet contains two compressed values as two nibbles. To get the value of the right nibble in the byte, which is the destination, we simply perform the bitwise AND operation with 0xf, as shown here on the byte. To get the left nibble in the byte, which is the source, we first perform the bitwise AND operation with 0xf0 on the byte, and then right shift the result 4 bits. Then we use the third index of the list bytes to get the length of the packet in the payload, and then we use the fourth index to get the expected checksum. To calculate the actual checksum of the packet, we use list slicing to calculate the sum of the payload space and then modulo 256. And if the checksum equals the expected checksum, the code passes to the next file in the folder packets. However, if the checksum is not equal to the expected checksum, the code first adds 1 to the counter and then open a new file in the output folder, which is named corrupted packets and the count, and then write this information in that file, including its source, destination, checksum, and expected checksum. And there we have one corrupted file identified. Here is how I solve part B of the problem. Since we have identified all the corrupted files from part A, all we need to do now is to construct the messages from the leftover uncorrupted files. The code begins by creating a new empty list named source destination, which is a list consists of different tuples. And then it iterates through every file in the folder packets to find the uncorrupted files by comparing checksum with the expected checksum, just like what part A did. And for every uncorrupted file that it identified, it will append the file's source and destination to the list source destination as a tuple. The code then goes through every unique tuple in the list source destination by using the set method, and then print out the source and destination of each message. For example, if I run this piece of code, it tells me that there are in total of 3 messages, with the first message having the source 9 and destination 3, and it also gives the source and destination of the other 2 messages. Here, 3 different dictionaries are created for each message to be constructed, and for each dictionary, there are source of the message, destination of the message, and message, which is another dictionary that contains the parts and the corresponding values to the part in each packet, and finally, the constructed message. Now, in order to regroup all the message in each packet into the original source and message that it belongs, I first put each dictionary for each message into a new list called messages, and then as the code iterates through all the files in the folder packets, it first identifies all the uncorrupted files by comparing the checksum with the expected checksum, and for each valid packet, it identifies if the source ID of the file is matches any of the source in the predefined messages. If a match is found, it then checks whether the part index of the file is already in the message dictionary in each dictionary for each message. If it is not in the corresponding dictionary for an entire message, then the code creates a new value assigned to the part index as a key to the dictionary of message. The code then uses the CHR method to convert the values in the payload space of the packets to actual text message and append the message to the part in the dictionary. After processing all the packets, the program moves on to reconstruct each message. It sorts the message parts by their part number to ensure the parts are in the correct order. The program then combines all the parts into a single reconstructed message. For each message, the program creates an output file named after the source device, writing the complete message along with the source and destination of the message into the file. When the program designed for part A is run, it generates one file for each corrupted packet identified and lists the file's source, destination, checksum, and expected checksum. Here are the files created for each corrupted packet identified. And when part B is run, it generates one file for each complete message that it constructed from the value in each packet. Here are the files created that includes the message constructed and also lists the file source and destination.